BBC4 Collections, archive programmes chosen by experts. For this collection, Professor Alice Roberts has selected a range of programmes to celebrate Horizon's 50th anniversary. More Horizon programmes and other BBC4 collections are available on BBC iPlayer.
These are what we call geodesic radomes, and they are designed to protect very powerful and important apparatus from the great storms of nature. We think of structures as being something very powerful, but these are very delicate. We think of eggshells as being very delicate structures. An eggshell is only 1/100th the diameter of the eggshell itself. These domes are 1/2 of that thickness. They're only 1/200th in their own diameter. Yet they've been through about 10 years of the most formidable conditions in the Arctic that any structures have ever had to stand. But I'm not a dome salesman. I'm an explorer in structures. I'm interested in the fundamental principles by which nature holds her shapes together.
Buckminster Fuller has a worldwide patent on his own way of holding shapes together. He is famous for his domes. They've made him $1 million. But at one time or another in the last 40 years, he's made front-page news as an architect, aviator, engineer, a sailor, a scientist, and a philosopher. But he is none of these by profession. He cannot be classified. He spans both the arts and the sciences in a way that few other men have done. Horizon aims to present science as an essential part of our 20th century culture, a continuing growth of thought that cannot be subdivided. So tonight, in this, our first monthly program, we explore this undivided, all-embracing world of Buckminster Fuller. A Cambridge scientist who knows him well is Dr. Aaron Klug. Dr. Klug has been working on the molecular structure of viruses for the last 10 years and first saw the relevance of Fuller's structures to his own work some 5 years ago.
Well, since that time, I have followed Fuller's work much more closely, and I have found a lot about his early experiments. I mean, he's a kind of an experimental mathematician. He's found a lot of things for himself. And I think this is his great strength, because he has made domes and other kinds of things. I mean, he's made cars and houses of various kinds, houses that hang rather than stand on the ground. He's done all these things, I think, because he has never been content with an ideal description of things. He's always set himself the rather strange problems. How would I do this given these materials and so on? He hasn't started from the limitations of mathematics or algebra or conceived notions. And he has also rethought all these things in a rather unique way.
Fuller's rethinking is certainly unique. As an experimental mathematician, he has had the satisfaction of seeing his experiments proved right. He explains some of the structural ideas that have been fundamental to his success to a group of students at the Architectural Association School in London.
I'm here in England visiting some scientists I've just come from Africa, and I'm on my way immediately afterwards to India and around the world. I've come to see these scientists, which would really be a fundamental interest to you as architects, because the structural exploration that I've been engaged in over a great many years has now become of interest to the scientists themselves. And I'm going to talk for a moment about structure. We're all very familiar with the rectilinear form, and children just making a first picture of a house are very liable to use this cube. But the cube does not really have structural integrity. There's some diagonals in each of the faces of the cube here, and they are really responsible for its holding the shape that it is holding. I'm going to take away the, disconnect the, I'm going to take this away, and we find that our cube has no structural integrity whatsoever. So, but this has not lost its shape. This is what was giving the cube then its shape. It is our friend the tetrahedron. And a lot of people say, why do you use the word tetrahedron? Simply because it means a system that has 4 faces, tetrahedron. The Greeks then have one word where we need to say 4 faces, figure with 4 faces, so that they're more efficient than we are, so we might just well use a nice efficient word. Now, if we try to make a whole shape, something you might say about shapes. Here are some energy actions in the universe. There are enormous numbers of energy actions in the universe. One of the things I've learned is that 2 actions can't go through the same point at the same time. It's like knitting needles. Like this. It's very important to recognize that. And I found that the scientists I'm visiting here in England are now very excited by the realization that new axiom, that 2 lines of action can't go through the same point at the same time, is really beginning to prove very worthwhile. Because every architect and every engineer has assumed that if you can put a point on the paper and you run a great number of lines through that same point. In fact, all the geometries, Euclidean geometry, all the non-Euclidean geometries assume planes with points and lines going through the same points. But I've given myself a discipline which whatever I use in the way of tools must be experimentally derived. And when the mathematician says to me, I'm a very pure mathematician, and I have a line that hasn't any dimension, I ask him why he uses the word line. Because the word line is an experience. It's a word derived from experience. And I say, why, if you're so pure, can't you invent a new word that's so pure that means whatever you mean, that has something that has no dimension, no experience? He hasn't thought about that. But anyway, when we then become empirical, we say then that we find that 2 lines can't go through the same point. And on the cover of this month's Scientific American, you'll see a picture of the cloud chamber used by the nuclear physicists in bombarding the nucleus. And you've read very recently about the discovery of omega minus. And what they do in the cloud chamber, bubble chamber, is to send in a very high-speed neutron or some other particle, and it suddenly collides with some other component, and then there is a parting of company, some angular resultants. And they're able to identify all the different nuclear components by the different kinds of angles that they take. Now, if 2 lines could go through the same point at the same time, then there would be no such interferences, there would be no such panels. Each one would just go through the other one, there'd be no breaking up in angles. So when we get down to the bubble chamber, we're getting down the very finest lines nature's ever made. And it actually is not a continuous straight line, it's a series of little bubbles. And it demonstrates very clearly that two actions can't go through the point at the same time. So that's why we have interferences and why we have reflection and refraction. And right, let's get two actions that get very close to each other. They get what we call critical proximity, the way the Earth is attracted to the moon. So you get a mass attraction. So once these two are attracted to each other that way, then we find that they could they'd be like a pair of scissors. They hinge together. Now we have an angle that is really an unstable kind of an angle, and what I would like to do is to have a stable angle so that I'll be able to have a persistent shape, and that's what I mean by a structure. So I find that I take a hold of this side of the angle, the other side, these are levers, and the further I go away from that fulcrum, the less effort it takes to stabilize that angle. So having come to the very end, we can take another action and let it cross here as a push-pull member. So with minimum effort, it stabilizes the opposite angle. So I find that triangle is a very extraordinary kind of device in that each side stabilizes the opposite angle with minimum effort. In other words, minimum effort is essential to the physicist because he finds that nature is always doing things with minimum effort. Now, we find then there are no other polygons that will do this. If I take out this, here's a square, we find it completely unstable, make more sides, this gets more and more, less and less stable. So that then the triangle is the only stable pattern, and now I'm going to want to do something which is, I'd like to develop then a local system that returns upon itself, that subdivides total universe into withinness and withoutness. And that is what I will then call a structural system. And in order to be able to have a withinness and withoutness, if I have two triangles hinged together like this, they simply come congruent. There's no inside and outside, too thin. So I find that the minimum subdivision of space is to have, say I have now two triangles. Again, it's like the hinge. I had a fulcrum before, now I have a hinge. So again, with minimum effort here, coming to the ends of the levers, I can stabilize that as opposite. So that becomes our friend, the tetrahedron. Unique then to the tetrahedron, to the system of omnitriangulated symmetrical systems is the fact that the minimum is with three triangles around each vertex. I can get four triangles around each vertex, and we call this the octahedron. You just count by counting off the faces, eight equilateral triangles. So always four. I can get 5 equilateral triangles around each vertex, and we call that the icosahedron. I can get 6 equilateral triangles around a common vertex, but they add up to 360 degrees. Therefore, it becomes a plane and goes to infinity and won't return upon itself. So it won't subdivide the universe locally into withinness and withoutness. So there are only 3 possible cases of omnitriangulated, omnisymmetrical, minimum effort shape stabilities. And that's tetrahedron, octahedron, and icosahedron.
The shapes that fascinate Fuller, the tetrahedron, octahedron, and icosahedron, are 3 of the 5 regular Platonic solids. There can only be 5 solids with their faces, edges, and angles all absolutely alike, and this fact has always fascinated philosophers. Plato thought that the 4 elements, earth, air, fire, and water, had atoms of these shapes, and that the 5th represented the vaults of the heavens. To the astronomer Johann Kepler, all 5 regular solids represented the heavens. By tracing, he believed, the orbits of the planets. The solution seemed so neat. The intense pleasure I have received from this discovery can never be told in words. But the discovery was just too neat to be right. To a practical man, like Alexander Graham Bell, the inventor of the telephone, these shapes were interesting not as solids, but as structural skeletons. In 1889, he addressed the International Academy of Science in Washington. I have come to the clear realization of the fundamental importance of the skeleton of a tetrahedra as an element of the structure of a kite or flying machine. Fuller wasn't interested in ideal Greek solids and knew nothing of Bell's tetrahedral kites. His interest stemmed not from flying, but from a childhood love of ships. Ships, said Fuller, do not survive unless designed to use winds, tides, tension, and compression to human advantage. In 1928, Fuller used these tension principles to design a 10-deck apartment house, using lightweight alloys and hanging the decks from a huge central mast. Delivery would be by airship. On approaching the building site, it drops its anchor and then drops a bomb. The 10-deck tower house is lowered into the crater like planting a tree. It's made fast with temporary stays until the concrete poured round its base is set. The airship then goes off to make a few more deliveries. One practical use Fuller saw for these tower blocks was as stopping off points on the great circle air routes over the globe. The towers could be carried to the most remote parts of the world. Using traditional building techniques was to Fuller quite absurd, but lightweight, mass-produced buildings were of no interest to the New York architects of the time. In 1930, Fuller was asked to speak in New York at a dinner given in honor of some of the famous American architects responsible for the new skyscrapers.
When I went to that dinner then, I knew that these other architects were famous. Everybody understood those big buildings, but what I was working on was quite invisible in 1930. When I stood up, I said, I'm working on the potential industrialization of the shelter industry, a time when the kind of industry that now goes into shipbuilding and in aircraft building might be applied to the production of buildings for men which could be even light enough to fly. And I said, what buildings weigh is not thought of today. Everything in industry is done on performance per pound. Is not so in the world of architecture and building. Just to prove that, we're very fortunate to have these famous architects here. So I said to Ralph Walker, can you tell me what the telephone company building weighs? And he said, no. I said, could you tell me just roughly within 100,000 tons? No. He said, could you tell me within 1,000,000 tons? And he said, well, he said, architects don't bother things like that. Then I tried each one of these famous architects, Ray Hood about his Daily News building and what the Rockefeller Center was going to weigh, what the Empire State and Chrysler building. None of them could answer it. So it was very clear that architects were not dealing in what buildings weigh. Therefore, they were not ratioing performance to the pounds, which is what you do in the development of ships for the sea and ships for the sky. And because of the high performance requirements of ships of the sea and ships of the sky, men are continually bringing in better alloys. The most advanced technology is brought to bear in that weaponry development in order to do more with less, to get the greatest hitting power, the greatest distance, in the shortest time, the least effort. I saw that over in that world of the advanced performance per pound, there might come a time when we could take the world's resources, which are serving only a very small percentage of humanity. By upping the performance per pound, we might be able to design a way of applying it to the home world where they were not considering performance per pound. And if we ever did, we might really be able to make the world's resources serve 100% of humanity at very high standards of living. When I sat down, Frank Lloyd Wright got up and he said, my young friend Buckminster is as good a designer as a bad speaker. And he felt this was very irrelevant to the other talking, but he made me his friend. From that time on, he always treated me as a friend and an expert on science. Frank Wright, in introducing me to his fellows at his Taliesin, said, I am an architect interested in science, and Buckminster is a scientist interested in architecture.
The explorers in architecture, like Frank Lloyd Wright, and the explorers in science, like Einstein, have always intrigued Fuller.
In the early 1930s, I had written my first book, and some publishers became interested and took the manuscript. And they wrote me a letter after a few months saying that some 3 chapters I'd written about Einstein made them feel that the book would have to be returned to me because they said they'd looked looked up the list of all the men that understood Einstein. There were 9 people at that time were supposed to understand him. They said, "You're not on the list." In fact, they said, "You're not on any list." And I'd have to then tell you what my 3 chapters were. My first one was explain Einstein's philosophy and how this motivated his going into his mathematics, and I explained his mathematics and how it translated this into his famous equation. Then I said, the individual scientist leads science. Science paces technology. Technology paces industry, and industry paces everyday economics. So that in the end, what the advanced scientist does, if it's really very important, affects all world society. It's quite a long lag in it. Therefore, I said, if Einstein's equations prove to be correct, because in the early 30s they had not been proven to be correct. So if his equations prove to be correct, then they will affect all world society. So my 3rd chapter was called E equals MC to the 2nd power equals Mrs. Murphy's horsepower. And I examined what would be the consequence in our everyday society if we accepted relativity and Einstein. The publishers, having written me this letter saying that I wasn't qualified to speak, I just thought of it quickly, and I wrote a letter and said, "Why don't you send my manuscript to Einstein?" And Einstein had just come to America in those days from Europe. He was at Princeton University. I forgot all about the incident. I expected pretty soon my publisher to send my manuscript back. When one day a doctor called me up in New York and said, "My friend Dr. Albert Einstein is coming in from Princeton this weekend, and he has your typescript, and he would like to talk it over with you." So I went to meet with the old man, and it was an extraordinarily moving meeting for a young man who thought so much of another man. And he said, "I'm going to write to your publishers and tell them I approve of your explanation of my philosophy and of my mathematics." But he said, this 3rd chapter, he said, "Young man, you amaze me. I cannot conceive of anything I've ever done having the slightest practical application."
Fuller has always been practical. 35 years ago, he saw the need for what he called an auto airplane, a jet-powered car that would fly. It was to have a triangular frame, rear wheel steering like a boat, and inflatable wings. It had to be aerodynamic if it was to fly, unlike the 1930s motor car, which appeared to be no great advance on the horse and carriage. The final design was intended to be a ground taxiing model for an auto airplane. A friend gave him some money and he rented a factory. Fuller and a yacht designer, Starling Burgess, set to work to build a 3-wheeled, 10-passenger vehicle powered with a standard V8 engine which was capable of 120 miles an hour. They built 3 prototypes, but the motor industry refused to back it. It was even refused space in the New York Motor Show of 1934. So Fuller parked it outside and caused a sensation. 10 years later, he got involved with industry again. This time, it was a circular house of aluminium and steel designed for mass production by an aircraft company. The house could be packed into a cylinder 22 feet high. It was suspended from a central mast held by steel cables. Each part was carried and fixed by one man. It took a few hours to build and cost no more than a Cadillac. But again, industry dropped the idea. These setbacks never deterred his exploration into structural geometry, which he carried on alone or with groups of students. It was with students, rather than with any big industrial organization, that Fuller developed his geodesic domes. The basic dome structure was achieved by subdividing the 20 triangular faces of an icosahedron.
1 and 20, and keeping these vertexes always at the same distance from the common center, we begin to get then spherical triangles. But you can see, even with your eye, this is an isosceles triangle. That angle is wider than these two are the same. There's an isosceles here, an isosceles here, and this is a symmetrical or equilateral. Now that has the quality of a propeller blade. That is, the center is symmetrical. The terminals, there are 3 terminals in perfect balance with each other, and they are, even though they're asymmetrical, they become a dynamic balance, like the propeller blade going around, each blade being the same. Now we can go on and make further subdivisions, which we do here. here will be the same icosahedron triangle. Now it has three. I had two subdivisions on the edge of the icosahedron triangle. Now it has three, and you can see the more of these subdivisions of the edge of the icosahedron, the more spherical it becomes, and the smaller each triangle becomes. And it develops a very extraordinary structural kind of a capability, because if I push in on one of these vertices, first thing I do is get to the dimple. If it's very high frequency, it becomes a very tiny little dimple.
In theory, the domes are strong and economic in material. Industry began to catch up with Fuller. They wanted to put his domes into mass production. This time, Fuller had hit the jackpot. The basic unit of this dome is an aluminium strut, 3 feet long, weighing 5 ounces. 19,680 of them, spanning 93 feet, and all designed to celebrate the 50th anniversary of the Ford Motor Company. Like a spider's web, 250 feet in diameter, another dome rises. This time for the American Society of Metals in Ohio. The domes went into mass production and began to spring up all over the world. An aluminium dome 145 feet in diameter was put up in Hawaii in 22 hours and recorded by time-lapse camera. In 1956, Fuller found himself involved with the United States government and the Cold War.
In 1956, the United States Department of Commerce was notified by the State Department that the British had found that in Kabul, Afghanistan, that the Russians and the Chinese and the Czechs and East Germans were spending a very large amount of money getting ready for a big exhibition at the Chechen Fair of Afghanistan, which is their great annual festival. And remembering that Afghanistan is bordered by Russia and China and India and Pakistan and so forth, it's a very extraordinary state. And the West was in there, but it was slipping out very fast, and the Russians were obviously courting them. We had no competitive exhibit. And the Department of Commerce was caught off balance. They didn't have any budget money for an exhibit, and no time, just 30 days were left. They came to me and asked if I could produce a geodesic dome within the 30 days, get it to Afghanistan in 30 days. They could only give me a very small amount of money to produce it, and we could only have one DC-4 to deliver it to Afghanistan, and send one engineer with it. That's all the weight would be permitted. The engineer arrived in Afghanistan, and he showed the Kabulians that were assigned to him to put it up. You put the blue to the blue, and the red to the red, and the green to the green. And the Kabulians didn't know what they were going to be, what they were putting together. It could have been a cube or any kind of a building, but suddenly they found they'd built a sphere. And the society tends to think of the people who put a structure up, the bricklayer or the carpenter, as being really responsible for that kind of structure. That the architect can ask him to various ways, but he's responsible for the structure. So the Kabulians, looking at their own Kabulians putting up a dome structure, said, "You're very good dome builders, aren't you?" So the Kabulians said, "Yeah, we're all right." And so they suddenly decided this was Afghan architecture because it had been put up by Afghans. It was simply a very large, new, modern unit of aluminum and plastic. And as a consequence, they fell in love with the dome. The exhibit inside was inconsequential. It was bouncing ball bearings and talking cow and things. And the people didn't pay any attention to that, but more than a quarter, more than the total inhabitants of Kabul showed up for the exhibit. And it became by far the most popular item in the fair, and way outperformed the Russians and the Chinese.
The Kabul dome has been flown to Warsaw, Casablanca, Istanbul, Tunis, New Delhi, Bangkok, and Tokyo, and is now on its way around the world for the second time. There are now over 4,000 of his domes dotting the Earth's surface, made of every material from metal to cardboard. But for Fuller, the success of his domes is merely one proof of his theories. What interests him now is the fact that his ideas have stimulated the thinking of many scientists. One of them is Dr. Aaron Klug.
In fact, the parallel between this and your dome is very close. I mean, it's fantastically close. They are based upon the same structure, although they realized in different ways. You have struts and tripods. Yes, we have rubber tubes and chemical bonds. But there's parallels even closer than that, because this is, so to speak, the distribution of matter, and this doesn't represent the real thing. After all, these bits of rubber tubing must be molecules which come together with chemical bonds, and these bonds aren't rigid things. I mean, they're more like a ball joint, although the angle is a certain preferred angle. And to represent, and moreover, when they come together, it must be done automatically.
You know my tensegrity structure.
Yes.
And that the three basics that come together really have that same relationship.
Yes, the same, yes, no, but what I wanted to say was this is another point, because I did notice that many of your domes in your book, you make a point that the dome in Kabul was put up by unskilled labor.
Oh, yes, right.
So because the Afghans are putting together the dome can't follow the complicated rules, you paint the ends. Well, we did a similar thing. I mean, almost, it was rather different. We have a different rule, which we call among ourselves Crick's rule. This is Francis Crick, who did some work on virus structures some years ago. And he always said as a joke, when we know what a virus is, a child will be able to build it. This model here, which is rather difficult to see, and you'll recognize it's your own D-sticks that are used.
Yes.
You know, remember Don Caspar, if you remember in Boston, he realized that you could use your D-sticks models for building this kind of tensegrity model. And now the rule you give to the child, or the unskilled persons, you join red to red and green to green. If I join red to red, I get that a dimer. If I join three of them, I get a trimer, three of them. If I join the greens, I get a hexamer, or pentagon, whichever way you like. And then you start building out, you build this extended net. I think this is one of the nets, the actual one of the nets you've used.
It is.
Yes. Well, I suppose if you make it by this rule, it must come out like this. Yes. Well, of course, we have a complication here. I mean, well, you know, if you have an engineering structure, you can put in the angles. But to make this more realistic, we have to have bonds at more than one level. Alternatively, we have to fix the angle slightly so the thing tapers round. So when you put the angles right, it'll fold up into this. Just the elasticity of your model makes up the spherical trigonometry. Exactly. Yes. You don't do any calculations. That's the marvelous thing about it. I mean, this is people often ask me, you know, can you do spherical trig? The answer is yes, but I don't use it. Not for this.
So what nature does when she puts this together in the simplest way, then she tries to get a little more comfortable, so she stretches into the spherical trig in due course, because there's just enough oscillating differences in it.
Look, there's one of these bonds has come undone, it's got broken, but the amazing thing is the thing hangs together quite well.
We find in all the geodesics you keep breaking open locally and just to have a local break, but that's all. It doesn't matter. The rest of the system is not bothered.
It's in equilibrium, yes. Right. And incidentally, one of the things that I think we've tried to teach electron microscopists is that shape, so to speak, is incidental. If the thing comes out to be whatever shape it turns out, we don't worry about fitting the shape. I mean, you know, people. It's amazing. People who are not used to these things. Because I discovered them for myself. I mean, it took me some time to realize that. A thing could turn out to have the shape of an icosahedron, actually look like an icosahedron, but in fact there are many rounded versions in which the triangles are spherical triangles. And this is, I really think this is a more or less incidental property. I don't know what you
I think it's so interesting something you just said, because I've given myself the problem of giving man some advantage of enclosures with a minimum investment. And I always say, I pay absolutely no attention to what they're going to look like.
Yes,
And when I finish, people tend to think of them as good-looking. They say that. But that's purely incidental.
Yes, well, I agree with you, absolutely, because this is the...
There's a function to be served.
Yeah, because this is an object, this is mathematicians like this object, but, I mean, well, one of the things I've learned from the way you make your things is that you abandon the traditional classical mathematics when you're discussing making real objects.
Right.
And although this is a sort of useful starting point, you've got to, well, you learn to forget some of the stuff.
Yes.
And that, in fact, in my own work was the hardest, well, it's the hardest step because, you know, I am a physicist by training, and I was, although I wasn't brought up in polyhedra because it was unfashionable, you know, I went right through school without knowing anything about these, and I had to learn for myself. But still, when I read the mathematical books, I always thought of an icosahedron as this perfect, you know, this, in the Greek sense, a perfect object. Now, I didn't ever think of it as made of, well, of course, when you see it, you see an edge, you actually see it as made up of real rods and struts and things, and this took some forgetting, I can tell you, because, in fact, one of the stumbling blocks that we had when we were trying to think of structures for spherical viruses, we made exactly this mistake. We always wanted to make the Greek ideal, and never the real thing. I mean, you know, nature doesn't care less about ideals. I mean,
it was in that way, for instance, I discovered that the two lines couldn't go through the same point at the same time.
Oh, yes,
so
well,
if that was so, then how is this physics made?
Well, exactly, yes.
Quite clearly, things won't be leading up to... and that really is the very essence of the skewing, is that things will not go through the same point at the same time.
Well, I must say, when I read your note, when I did see your notes, and I read one of your theorems, that two lines can't intersect, you know, it seems a bit odd, you know, and the first tendency is to laugh at it, of course, because this is not what one learns at school. But when you think of the real world, the world of objects, you realize this is absolutely bound by this, you know, and I have learned that.
I think we were shown that in the cloud chamber.
Dr. Klug and his American colleague, Dr. Casper, have studied Fuller's work in great detail. Recently, Fuller met for the first time an electron microscopist working on the structure of certain biological enzymes, Robert Horn.
Structure of some basic proteins in the electron microscope. They're much smaller than virus particles. In fact, the size of the protein is equivalent to some of the small units that people have been seeing on the surface of viruses. This particular protein is what we call an enzyme. It's a type of catalyst. It has properties of breaking down chemical components in biological systems. And this particular enzyme is an extremely small one, and it is known as glutamic dehydrogenase, a rather long...
Will you say that once more for me, sir?
Glutamic dehydrogenase, it's protein with a molecular weight of about 1 million. And in the electron microscope, in some of the preparations, we see these roughly triangular-shaped particles, and in some cases we see a number of sort of V-shaped or U-shaped units. Well, this, you can see the sort of problem. We're right down now to molecular levels, and we have a pretty strong suspicion that the tetrahedral symmetry is coming up again.
Yes.
We found the icosahedral symmetry, as you well know, in the viruses, and going down even further, we're pushing the microscope more or less to its limit here as to what we can see directly. And I find it very fascinating anyway that this type of arrangement is coming up over and over again.
And at the Massachusetts Institute of Technology, a professor of crystallography confronted the computer with the question of what the coordinate system was. You know about this, Dr. Loeb, and the computer came back and said that nature in crystallography was really using 60-degree coordination instead of 90-degree coordination, which seems to be quite exciting because this brings us back to our tetrahedron.
It comes back again.
Yes.
Yeah. I think there are a number of instances where we have this threefold symmetrical plan. But the thing I wanted to perhaps ask you as a matter of interest to creating order out of disorder like this is, what are the possible configurations? Could you build it perhaps of 3 or multiples of 3? Or are there other arrangements in the tetrahedron?
You could, of course, do it with 6, the 6 edges of the tetrahedron. But, I find that you can do it very beautifully with 3.
With 3?
Yes.
Now this is putting two units rather than 3 together.
There are two units, which are, you can see this form.
Yes.
I call this an event. I call central line here, this is an action, this is a reaction, this is a resultant.
Yes.
They're necessary to all actions. There be reactions, resultants, and they do not occur in 180-degree planes or lines. There's always a precessional effect, so that this I'd call a negative event, and then there's a positive event, and those come together and give you a tetrahedron.
Another tetrahedron. So we could in fact have a protein which is folded in this way, the angles being reasonably constant throughout.
Yes.
But it would have a positive and negative nature.
Yes.
For many of the scientists who have met Fuller, the experience has been rewarding. He does not set out to copy nature, but he is pleased, though not surprised, that scientists are finding that nature's solutions to her own structural problems coincide with his.
This ping pong ball is quite translucent. You look at the light, you can see the light coming through it. The only reason light can come through it is full of holes. Simply the holes are smaller than the human eye can see. So inasmuch as it's full of holes, it turns out to be all triangulated, and it is a geodesic structure. In the same way, then, we know that smaller and smaller things get to be are also full of holes and are taking the most comfortable geodesic positions. Therefore, it becomes very interesting to get down, for instance, to the cornea of the human eye. Dr. von Hochstetter has been succeeded in staining the membrane of the human eye cornea, and we find that it too is very clearly a geodesic structure, a tensegrity geodesic structure. Then we get down much smaller still, down to the size of the little animals in the water called radiolaria, and we find, again, its structures are geodesic structures. They are also usually on the icosahedron, but sometimes the octahedron, sometimes on the tetrahedron. Then we get, at the same level, those little animals, we have some little plants called the diatoms, or the algae. And this picture was taken with the electron microscope in the Max Planck Institute by Dr. Helmke. And you'll see it too is a geodesic structure.
A microorganism has the same basic structure as his 2-mile diameter dome project over Manhattan. The same principles work on any scale. At the age of 68, Buckminster Fuller is still exploring. Behind all his varied explorations stands the promise he made to himself in 1927, to discover the principles operative in the universe and share them with his fellow men. He has never pursued novel structures for their own sake. He is determined to do the most with the least, not as an intellectual exercise, but because he firmly believes that the possibility of the good life for any man depends on the possibility of realizing it for all men.